Hello, my name is Josh Daymude,
I'm Noble Harasha.
and we'll be presenting our results on deadlock and noise in self-organized aggregation without computation.
When it comes to swarm robotics, being able to minimize the capability of the individual robots in your system um, allows these systems to be more feasible and effective at smaller scales. You can imagine at very small scales of operation, your computational and memory resources are a lot different and limited. So being able to minimize the capabilities of your individual robots is very important. The general problem we are talking about here is swarm aggregation, which is defined as given some number of robots in arbitrary initial positions. We are defining a controller to be run by each individual robot such that eventually all robots aggregate together to form a single connected component that ideally is as compact as possible. And this is obviously a very well-studied problem in swarm robotics.
In 2014, Gauci and others introduced a surprising algorithm for swarm aggregation, where every robot only needed a single line of sight sensor that said whether it saw another robot or not. The algorithm did not need any persistent memory, and it didn't even need kind of in-the-moment arithmetic computations. So it was able to do all of this with just a binary line of sight sensor. And their controller is defined as a four tuple. Each member of this tuple is just a speed, one for the left wheel, one for the right wheel, and for each of those, one for when the robot sees something and one for when it doesn't. So these are just four numbers between -1 and 1 for backwards and forwards. And using grid search to look at a whole bunch of possibilities for the controller, they decided that the best one for aggregation was this one here, which when translated just kind of conceptually, there's essentially two rules. One, if you don't see another robot, then rotate clockwise around a center of rotation, trace out a circle. Otherwise, if you do see another robot, rotate clockwise in place. There are two theorems, main theorems in their paper that gave good performance guarantees. The first is that a single robot using this controller will always aggregate to either another robot in place or a static cluster of robots in place. Secondly, two robots both using this, so both moving, will also always aggregate to one another. In simulation, they showed that this is also true for arbitrary size systems. So you can see here that over time, the actual experimental robots are aggregating using this algorithm. However, it was never proven that any system of n greater than 2 robots would definitely aggregate using this algorithm.
And this open question of whether a system of some arbitrary size n greater than 2 robots, the question of whether that's guaranteed to aggregate using this controller is the foundation for everything we're going to be looking at. So our contributions can be outlined as follows. So first, we prove that this conjecture does not hold in general. And we do this by defining deadlock configurations in which aggregation is impossible. Next, we demonstrate the algorithm's robustness to certain amounts of error and noise in both its sensor and its general movement. And finally, looking at cones of sight, instead of the original lines of sight, first we prove a linear aggregation time for systems of n equals 2 robots, which means this is a linear speedup over the system, the n equals 2 robot system using lines of sight. And we also look at larger systems and demonstrate faster aggregation time as long as the cones of sight are small enough.
So we'll start with our first contribution, which is identifying deadlock configurations from which aggregation is impossible. In particular, we show that these are deadlocks for all clockwise searching controllers. And that's a class of controllers, which the one that we care about belongs to, but it's broader. And how it looks is as follows. For even numbers of robots in the system, we essentially pair them up 2 by 2, and we set them so that all of their lines of sight, which are these dotted arrows, are all pointing such that no robot sees any other robot. And that means, by the algorithm, that each of these robots is trying to trace out its circle. It's trying to move around its center of rotation. But then we pair them up in such a way that they want to move exactly into one another's position, so these forces cancel, and no movement is happening whatsoever. So because of this, the system will remain disconnected and disaggregated indefinitely. When the number of robots in the system is odd, it's a very similar idea. We pair up all the robots that we can, and then at the end, instead of having a final pair, we have a final triangle, and we rotate them so that once again their forces cancel, and they're never able to make progress. So this shows that in theory, there do exist configurations from which this algorithm will not achieve aggregation. In practice, of course, with real robots, the physics of collision and sliding that happen in the system will make these sorts of things, they would slip past one another. But in theory, these are indeed deadlocks. Now, there was a second kind of obstacle to aggregation that was proposed by Aaron Becker at the Dagstuhl seminar where this work was originally formulated. And Aaron was worried about Livelock. So these robots would continue to move, but they'd be trapped in these symmetric traversals indefinitely, never reaching aggregation. The original idea was if they were set up in some perfectly symmetric situation, and so that applies both to their positions and to their lines of sight, that they would be trapped in some sort of circular dance, like the one you're seeing here, forever and ever. However, we find that, purely by simulating these things, that lo and behold, if you run these long enough, they will still aggregate. This is shown by the graph on the right. Dispersion is one of the metrics that we use to measure aggregation, where a dispersion of 0 is no distance between robots whatsoever. And you're seeing that regardless of the number of robots, even though there is this kind of periodic motion that happens with this dance, those periods are getting smaller and smaller until they reach their aggregated positions.
Here, we're looking at a system of 100 robots, all running the algorithm. And on the right side are some different aggregation metrics plotted over time for the simulation you're seeing on the left. The first three, which are all declining, are just different measurements of how compact or how aggregated the robots are. And the final metric, cluster fraction on the bottom right, measures how connected it is. So, a larger cluster fraction would be more connected, more compact. And as you can see in the video on the left, all the robots over time are eventually reaching some aggregated configuration, as would be expected. As previously talked about, we're not seeing any of the deadlock due to the physics of the system. So in practice, these just arbitrarily large systems do indeed aggregate consistently. Next, we look at the algorithm's robustness to error and noise in both its sensing and its motion. So in the previous run of the previous slide, that system had no explicitly added noise. The only noise you could think of is, just the physics and the collisions and such. And here we are explicitly adding noise to the system. The first form of noise we look at, we call motion noise, which at each time step, each robot is experiencing some force of a random magnitude between 0 and m star, which is some parameter we're defining and changing, in a random direction. And the figure on the left is looking at this motion noise. So on the x-axis, we have the amount of noise. And on the y-axis, we have the time to aggregation. Each circle there is a single run of a system. So as you can see, for a reasonably small amounts of noise, we're getting consistent and flat runtimes, showing it's robust to that amount of noise. But at a certain point, around a max force of around 20, the runtimes start to increase, and eventually many of the systems, many of the runs are not aggregating at all. So the takeaway from this, certain amounts of noise are okay, and our algorithm can withstand that. But at a certain point, if you have too much noise, you're really not even running the algorithm. The behavior is nearly fully chaotic. The second form of noise that we look at is error probability, which represents noise in their sensors. So each robot at each time step has the same probability P of receiving the incorrect feedback from its site sensor. And it's worth noting that this is the same thing as sensory noise, as was looked at by Gauci, as long as you think about false positives and false negative probabilities as the same. And looking at the figure for error probability, once again, if there's too much noise, runtime gets unreasonably long and the systems are not converging. But again, there is some range, there's some small amount of noise in which the algorithm is still aggregating and is robust to that noise.
So having established that the algorithm has theoretical deadlocks, but in practice is not only good at aggregating, but also is good at aggregating when noise and error are present in the system, the last thing that we want to look at is what happens if the robots are given slightly more information than just a line of sight sensor. What if instead they were given binary cones of sight, where they see a conic region of the plane, where the size of this cone is just some angle beta that we're in control of. So what is this going to do? On one hand, the bigger beta is, the more information they're getting, right? The more of the plane that they're seeing. But on the flip side, since this is still just binary, is there somebody else there or is there not? The specificity of this information is decreasing. If I have a whole half plane of information and the answer is yes, I have no idea where the other robot, or if there are multiple robots in that direction. I just know that there's somebody there. So in simulation, this is what this looks like. And we're seeing that the biggest important thing here is that when they rotate in place because they see someone else, they're rotating further than they did before. This is because they always have to rotate at least the angle of their sensors. And this actually allows them to make more progress towards aggregation more quickly. Already, even after 20 seconds, we're almost aggregated. And we see this for larger systems in general here. So lines of sight are at this 0 mark where the angle of the sensor is 0. And we see that going from 0 up to 0.5 rads, or about 30 degrees, for all systems, regardless of size, from 10, 50, 25, 50, or 100, the runtime is speeding up. We're getting better aggregation times with more information. However, especially for these large systems, like the n equals 100 one, too large of a cone of sight is actually hurting runtime. And this is because the amount of time you spend just rotating in place instead of actually moving and making progress towards aggregation is really high, because you're just seeing people all the time. So to complement these simulation results, we also prove a theorem. This is for the 2-robot case, where one robot is moving according to the algorithm, the other is just standing still. And here we're giving that moving robot a cone of sight sensor of size beta. So this generalizes a similar theorem that Gauci originally had. And we prove that aggregation is achieved in a number of rotations around its center of rotation that is upper bounded by this expression here. And the important part of this expression is that it depends linearly on d0, which is the initial distance between the 2 robots. The line of sight situation actually depends on d0 squared, So we get a linear speedup with cones of sight of any fixed size greater than 0, which is a linear improvement over the original result. So that's all we have. Thank you very much for your attention. We'd like to thank our funding and also for the Dagstuhl Institute that hosted the original workshop that inspired this work. So thanks very much.
Thank you.